Good afternoon, class. We're looking at Chapter 4, Application of Derivatives, Section 4.2, how derivatives affect the shape of a graph. So we looked at maximum and minimum values, and now how derivatives affect the shape of a graph, reminding you of differentiation formulas, definition, various formats of definitions. For example, f prime of x is limit of f of x plus h minus f of x over h as h approaches 0. Definition of an E in a couple of different formats. The power rule, the derivative of x to the power of n is nx to the power of n minus 1. And then some trigonometric functions such as the derivative of sine x is cosine x, and so on. Some properties and theorems involving the product rule, the quotient rule, the chain rule, the extended power rule, how to differentiate exponentials. In short, you start with the function itself and then move on with more. Logs, how you differentiate them. If you happen to have a curve, delta y is rise along the curve, dy is the rise along the tangent line. So delta y is f of x plus delta x minus f of x, which is this distance bq. dy is f prime of x dx, which is this distance ab. And sometimes we use dy to approximate delta y. Also, linearization simply means find the equation of a tangent. So I would use the point slope. You can develop it into that, or you just leave it as the point slope and then simplify. In other words, you don't have to memorize that. Also recall, local minimum occurs at the point C in an open interval of a to b in the domain if f of c is less than or equal to f of x for all x values in the open interval. That's the key. Local maximum occurs at the point C in an open interval of a to b in the domain if f of c is larger than or equal to f of x for all x values in the open interval. So if we look at this, basically peak is the local max and valley is the local mean in both cases. Absolute, also known as global extrema. Absolute minimum occurs at the point C if f of c is less than or equal to f of x for all x values in the domain. Absolute maximum occurs at the point C if f of c is larger than or equal to f of x for all x values in the domain. The difference is this happens in some open interval. This is in the entire interval. So when we look at those, understand peaks and valleys, they're always local. Local mean, local max, local mean. Local max, local mean, local max. This one doesn't, there is no other point having a smaller y coordinate, so it becomes an absolute minimum. And this one, there's no other point having a larger y coordinate, becomes an absolute max. What is a critical point? A critical number or point of a function f is a number such that f prime is 0 or f prime does not exist. What is the process? Find f prime, set it equal to 0, find the answers. Also where f prime does not exist. Those are the possible critical points. Now, extreme value, also known as closed interval theorem. If f is continuous over a closed interval of a to b, then f has a maximum and minimum value over the interval. What is the method? First, we have to verify that f of x is continuous on the interval of a to b. Then we find all critical points. How do we find it? F prime is 0 or doesn't exist, this concept. Then we evaluate the function at the endpoints a and b, as well as all the critical points. Absolute maximum equals the largest value. Absolute minimum is the smallest value. That's how we arrive at the answer. Here's the summary of the section 4.2. How derivatives affect the shape of a graph. Theorem. A function is increasing where f prime is positive. A function is decreasing where f prime is negative. So as we look at this two, obviously, it's a curve, but looks almost like a line with a positive slope, so increasing. This is a curve, looks like almost aligned with a negative slope. Definition: a critical point C of a function is a point of which f prime is 0 or f prime does not exist. A relative max or relative mean is a critical point at the top or bottom of an interval of a graph, peaks and valleys. A function is concave up where f double prime is positive, which means f prime is increasing, and it can hold water. A function is concave down where f double prime is negative, which means f prime is decreasing. It cannot hold water, as you recall from pre-calculus. An inflection point C is the point where concavity changes. Inflection points occur where f double prime is 0 or does not exist. So, for example, right here, this is concave down, and it changes to concave up at the point where the change occurs. It's the point of inflection. Now, concave up, the graph of f of x lies above all its tangent lines on an open interval. So, for example, if you look at these two, concave up, you see the graph is above the tangent line. We have only one in this case. Same here. However, when it's concave down, the graph of f of x lies below all of its tangent lines on an open interval. So if you have one, you see that this is below. For this one, this is below. Furthermore, if we have more than one, for example, in this case, we have one here, we have one here. In this case, we have one here is above that. So for concave upward, slopes of tangent lines increase. Notice this one has a positive slope, this line segment, which is a tangent line. So does this one, but this is steeper, so it's larger. This one has a negative slope, so does this one, but this is steeper, so this is more negative than this one. So it's increasing, and we say f double prime positive. That means f prime is increasing, concave up. On the other hand, if we look at this case and we have a couple of tangent lines, this has a negative slope. This also has a negative slope, but this is steeper. This is more negative than this one. So for concave downward, slopes of tangent lines decrease, become smaller. This one and this one, both of them have a positive slope, but this one is obviously steeper than this one, so this is more positive than this one. So again, slopes of tangent lines decrease in this case, and we write f double prime less than 0, f prime is decreasing. Also, a point P on a continuous curve f of x is an inflection point if f of x changes concavity. For example, right here, concave down, then concave up. This is the point of inflection. This one is first concave up, then concave down. Again, point of inflection. Steps to curve sketching in addition to pre-calculus. In other words, we use the prior knowledge of mathematics. For example, the intercepts, the end behavior, the behavior near an x-intercept. We discussed that. In addition to that, now we are going to add calculus. Find relative maximums and minimums and intervals where the function increases and decreases. Set f prime equal to 0, solve for x, and make a sign graph. What is a sign graph? A number line and test values between critical numbers. Find inflection points. How? Set f double prime equals 0 for and solving for x, and again you make a sign graph. Find possible inflection points, IPs for short, and where the function is concave up or concave down, and sketch the graph. In other words, use prior knowledge of mathematics, meaning intercepts. X is 0, find y. Y is 0, find x. Those are intercepts. Okay, when x is 0, you have the y-intercept. When y is 0, you have the x-intercept. And as I mentioned, the end behavior and behavior near an x-intercept. Then we use a sign graph on f prime to see where the function is increasing, decreasing. Does it have a local max, local mean? And we do it for f double prime as well, and it shows us where the function is concave up, concave down. Does it have an inflection? So that's the process. Extreme values of a function are created when the function changes from increasing to decreasing or from decreasing to increasing. Note, the function is increasing first. Then it becomes decreasing. What's in between is an extreme value. More specifically, it's a peak, it's a local max. However, if it's decreasing first, then increasing, again, in between we have an extreme value. This one is a local minimum. Look at this one, decreasing, increasing, decreasing. What happens in between? Extreme value, same here, local mean, local max. Over here, increasing, decreasing, increasing, decreasing. So increasing to decreasing, we have extreme values at the peaks and valleys. This is local max, local mean, local max. Therefore, we're going to write a function is increasing where f prime is positive and decreasing where f prime is negative. Now, this can be proved using MVT, the mean value theorem. You're not responsible for that. I'm going to quickly mention that. According to MVT, the mean value theorem, if f is a continuous function in the interval of a to b, closed interval, and f is differentiable, DIFF, differentiable on the open interval of a to b, then f prime of c equals f of b minus f of a over b minus a. What do we mean by that? Let's take a look at this graph. You have a curve, and you know this is a continuous function from a to b, and it includes the endpoints a, b. That's what this means. Because it's a nice and smooth curve, therefore it makes it differentiable in the open interval. Now, if you connect these 2 points, it creates a line, we call it the secant line. And what is the slope of the secant line? F of b minus f of a over b minus a. And we are saying because it's continuous and because it's closed, somewhere in between there must be a point that you can draw a tangent line. That means take the derivative f prime of c at that point, and it must be equal to the slope of the secant line. That means the two lines must be parallel. That's what it says. And now if we do the cross product here, we get f of b minus f of a equals f prime of c times b minus a. They are identical, okay? They are equivalent. Also, an easy way to understand increasing. As x gets larger, notice from left to right, x gets larger. If y gets larger, we say the function is increasing. If it gets smaller, we say it's decreasing. Obviously, the choice of a and b, when you write it in this format, obviously b is on the right and a is smaller than b, or b is larger than a. So if b is larger than a and f prime is positive, that means f prime of x is positive everywhere, including at c. So what is f prime of c? F of b minus f of a over b minus a, larger than 0. If this fraction is 0, and the bottom is 0 because b is larger than a, the numerator must be also larger than 0, which makes f of b larger than f of a, which makes it increasing according to the definition that was mentioned. This is actually the proof of the concept of increasing, decreasing. What is the first derivative test? We find y prime when it's positive, the curve is rising first or increasing. Then if it's decreasing, that means f prime is negative, it's falling, it creates an extremum. And we said that's a local max. But if it's the other way around, that means F prime is negative first, curve is falling, decreasing, and then positive second, curve is rising, that means increasing. Again, it creates a local extremum, but this time it's a local minimum. That's it. So how do we go about coming up with the first derivative test? First, y prime or f prime is zero, it doesn't exist. That would be possible local max or mean. And we use sign graph for this test. And that's the idea. You always use a sign graph, everybody. Now, we also have concavity test and second derivative test. Those two are different. What is the concavity test? You find y double prime. When it's positive, it's concave up. That means it can hold water. When it's negative, it's concave down. And so when the change occurs, that's a location of an inflection point. Where do you find the inflection point? Possibly at f double prime equals zero doesn't exist. So a function is concave up where f double prime is positive. That means f prime must be increasing. And it's concave down where f double prime is negative. That means f prime is decreasing. And we use sign graph to check it out. Second derivative test should not be mixed up with concavity test. It gives you half of the information of the first derivative test. Remember, with the first derivative test, we have to find the critical points. Now we evaluate f double prime at those critical points. And we know it's concave up when it's positive, down when it's negative. So when you plug in the critical point and it becomes negative, it means concave down. Concave down looks like this. So what is this? Local maximum. On the other hand, if it's positive, it looks like this because it's concave up. So that's a local minimum. So this is an excellent test for applications, not necessarily for graphing. Recall, this is from pre-calculus. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. In other words, a polynomial is in the form of f of x equals a sub n x to the power of n all the way to a sub 0. And eventually it'll look like its leading term a sub n x to the power of n. That's what we are saying, everybody. Now, as we look at these four graphs, even power, odd power, so if a sub n, the leading coefficient, is positive, it looks like y equals x squared, which means whether x goes to positive or negative infinity, y goes to positive infinity. If a sub n is less than 0, the leading coefficient, f of x looks like minus x squared, which means whether x goes to positive or negative infinity, y or f of x goes down to negative infinity. If it's odd power, looks either like x cubed or minus x cubed. In the case of x cubed, if x goes to positive infinity, so does y, or f of x. If x goes to negative infinity, so does y. So we have the first and the third quadrant as the end behavior. Whereas here we had the first and second, here we had the third and fourth. And if f of x is minus x cubed, we have the third and fourth quadrant. My apologies, second and fourth quadrant as the end behavior, meaning when x goes to negative infinity, y or f of x goes to positive infinity. When x goes to positive infinity, y goes to negative infinity. We also have behavior near a zero and it has a multiplicity. This is a theorem. When x minus c is to the power of m, m is the multiplicity, the number of times it gets repeated. If m is odd, f crosses the x-axis at c0. If m is even, f does not cross the x-axis at c0. So as we look at this, by the way, over here they use p and m are the same. So normally m is a better, m stands for multiplicity, but in some texts they use p. M is, or p is 1, so it crosses. 3 crosses. Even. 2 doesn't cross. The higher the multiplicity, the flatter the curve is at this 0. The sum of the multiplicities is the degree of a polynomial function. So pretty straightforward. Let's use all of this information, including calculus, to graph this function. Example 1, sketch the graph of y equals x cubed minus 3x squared plus 4. They happen to give us the factored form for the sake of intercept, x-intercepts class. If they didn't, we have to come up with that. So what I want to do first and foremost, I want to remind you how we graph this in pre-calculus. So it can be done without calculus, but calculus will make it more precise. Here's what we've done. First, find the intercept. I hope you see this is the easiest one for the y-intercept, the constant 4, that means 0, 4. And for the x-intercept, you see, for the y-intercept, x is 0. For the x-intercept, y is 0. So this is minus 1, 0. This is 2, 0. As I mentioned, this is 0. We have those points. You don't have to be too scared. You get the picture. So this is what we know. What else do we know? Well, this has multiplicity too. That means it can't cross. Also, this gives me the end behavior, the first and the third quadrant. So if I put all of them together, the graph looks something like this. And if need be, you can pick up more points. What does calculus do for us? It shows us the exact location of the peak, because it may be like that. It may be like this. Or it may be like this. Which one? We'll find out with the help of calculus. But practically, we have the graph. So we're going to add calculus. And to do so, we are going to go with relative extrema, starting with the CPs for y prime. To do so, let me erase my work. Y prime is 3x squared minus 6x. To set it equal to 0, we factor 3x out. So 3x times x minus 2 equals 0. And of course, this means x is 0, x is 2. Now, we are going to do the first derivative test, which means we use a sign graph. What is a sign graph? A number line from negative to positive infinity. So x, the independent variable is x in this case. Anything that is, it's going to go from negative to positive infinity. The function that you are doing the sign graph could be f of x, f prime, f double prime. In this case, first derivative test, you must use f prime. Then the critical points, you put them here from smallest to largest. It always must be in order. So you put 0 and 2. At x equals 0, f prime is 0. At x equals 2, f prime is 0. So you put those values. Now, for the first derivative test, we just want to know what happens in between. So 0 and 2, two critical points give us 1, 2, 3 sub-intervals from negative infinity to 0, 0 to 2, 2 to infinity. So what do? We pick up TPs, short for test points. So to the left of 0, I'm going to pick -1. In between, I'm going to pick 1. And over here, I'm going to pick 3. So basically, you put this number either into y prime in the given format or in factored form. Sometimes factored form is easier. You really don't want the number. You just want to know the sign. So when we plug in -1, 3 times -1 squared is +1 becomes 3. -6 times -1 is +6. They add up to 9. Doesn't matter it's 9 or 9,000. The point is it's positive. Let's plug in 1. 1 squared is 1 times 3 is 3. This is -6 is -3. Again, doesn't matter it's -3 or -3,000. The fact is that it's negative. And finally, you put number 3 and it gives you positive again. So we're going to write positive, negative, positive. Now, before we move on, I want to make a point, and that is if the factored form has each factor with exponent odd, it happened to be 1, then they will alternate as long as you come up with one of them. So when you come up with this, they will alternate, or come up with this, you don't have to do all of them, but you have to be very careful with that. Now, what does it mean? I'm going to use up arrow for positive, down arrow for negative. It makes it easier for me to see that up and down, this is a local minimum. Down and up, local maximum, my apologies. It goes up and down. This is the peak. Local maximum occurs at 0, down and up. Local minimum occurs at 2. Just the arrows will tell you what happens. So if the local maximum occurs at x equals 0, you have to put it back into the original equation. You already know 0, 4, so that means 4 is the maximum. So you write local max equals 4 at x equals 0 over the pair. What about minimum? Is 2 at x equals 2. Plug it into the original one. You already have 2, 0. So that means the minimum equals 0. So you write local minimum equals 0 at x equals 2 or 2, 0. Furthermore, the function negative means decreasing from 0 to 2. Positive means increasing from -infinity to 0, union 2 to infinity. And you write that. So as you can see, we get a lot of information from the first derivative test. For the graph, you really shouldn't do the second derivative test. I'm going to show you what it does, because it does half of the job. And I'm going to remind you again, when f double prime is positive, it means concave up. That means relative minimum. And when it's negative, concave down, that means relative maximum. I'm going to elaborate on that in a moment. But again, don't do the second derivative test for graphing. It's an excellent tool for applications. We will see it later. So we already established that y prime is 3x squared minus 6x, and the critical points are 0, 2. And let's find y double prime, 6x minus 6. And the second derivative test says, just plug in those values to see if they are positive or negative. So if I plug in 0, I get -6, which is negative. Again, it doesn't matter, -6 or 6,000. The fact that it's negative, the graph is concave down. Looks like that. What is that? Local max. So graph is concave down. 0, 4 is a local maximum. On the other hand, if I plug in 2, I get +6. Positive looks like that. Concave up. Concave up, that means local minimum. So graph is concave up. CU short for concave up. 2, 0 is a local minimum. So where is the function increasing, decreasing? We have no idea. The first derivative test does that for us. That's why you don't want to do this. But I just wanted to emphasize what it does for us. However, we want to go with the next piece, which is finding inflection points. set f double prime equals 0, and solve for x, make a sign graph. We already have y prime. We already have y double prime also from the previous page, so we don't need to do it again. Set this equal to 0, and x becomes 1. Now we are going to do a sign graph because we remember when f double prime is negative, is concave down. When it's positive, is concave up. And possible inflection point occurs at whatever this x is, x equals 1. We need to do a sign graph. Again, what's a sign graph? A number line from negative to positive infinity. What is the independent variable? It happened to be x. What function are you working with? In this case, I'm working with y double prime. So x goes from negative to positive infinity. The function we are working with is the second derivative. And at x equals 1, y double prime is 0. So this number 1 cuts it into two sub-intervals from negative infinity to 1 and 1 to infinity. So we use a test point on each side. Obviously, the easiest point to the left of 1 would be 0. And to the right, let's use 2 or any number you want. So we're going to plug in 0. When you plug in 0 into y double prime, obviously gives you negative. We want the sign, negative, which means concave down from negative infinity to 1. If we plug in number 2, we get positive. Positive means concave up from 1 to infinity. So we write it's concave down from negative infinity to 1, concave up from 1 to infinity. Because of the change, number 1 is the point of inflection. What is its y coordinate? Put it back into the original function. It's easier here. If I put 1 here, I get 2. 1 minus 2, I get negative. 1 squared is positive. 1 times 2 is 2. Therefore, 1 comma 2 is the location of IP and inflection point. We have everything. We have all the intercepts where the function is increasing, decreasing, local extrema, where the function is concave up, concave down, inflection point, we can graph. So what you see here, the reminding you what we did, the function y equals x cubed minus 3x squared plus 4, or x plus 1 times x minus 2 squared. Y prime is 3x squared minus 6x. Y double prime is 6x minus 6. Intercepts located at minus 1, 0, 2, 0, 0, 4. Increasing from negative infinity to 0 union 2 to infinity, and decreasing 0 to 2. Concave down from negative infinity to 1, concave up 1 to infinity, inflection point at 1, 2. Let's make up a summary table. So we put the numbers in here. We have the x-intercept, the y-intercept, the inflection point, the other x-intercept. This extra point is not a must, but let's say you want it. So if I plug in 3, it's easier here. 3 plus 1 is 4. 3 minus 2, 1 squared is 1. So just 4. So we are going to locate each and every pair. Minus 1, 0 is here. 0, 4 is here. 1, 2, 1 to the right, 2 up is roughly here. And by the way, we do a double-sided arrow because it's a maximum. It can't cross that. This is 1, 2. The minimum is at 2, 0. And again, because it's the minimum, we put a double arrow that cannot cross it. Extra point 3, 4 is here roughly. Also, if you look at the original function, the leading term is x cubed. So the leading term is x cubed. The end behavior depends on the leading term because n equals 3 is odd and a sub n or a sub 3 is 1 positive. Then we are looking at the first and the third quadrant. So that would be the graph as expected.